Hello and welcome to the Web3 Advocate channel. Today, we're diving into Uniswap version 4 and its latest features and improvements. Whether you're a developer or just curious about DeFi, this video will help you understand what's new, what's changed, and how everything works under the hood. Let's jump right in. Let's overview the four modules of Uniswap 4. Core module, which consists of the fundamental pool logic and holds all state updates. Periphery module is built on the top of core module. It wraps the raw pool logic with user-friendly features and it handles all liquidity-related operations. Universal router module is the main trade entry point for users and routes across multiple protocols. With every successful trade, the core state gets updated. It allows liquidity pools from formal versions to upgrade to the current version. Hawks module, on the other hand, are external smart contracts that can be attached to liquidity pools to customize and extend the pool behavior. It consists of various flags. If any of these flags are selected and turned on, they should be specified at pool creation. Some of these flags are liquidity and fee-related flags. Before we dive deeper into the innovations of Uniswap 4, let's rewind for a moment to see how things worked in version 3. A liquidity provider would start by calling the create pool function on the factory contract, which spin up an entirely new contract for each pool. Each pool contract had to manage its own state and fee structure independently. Every single pool was a standalone contract. Once the pool was created, the provider then had to call the mint function on the position manager contract. This minted an ERC-720 token that represents the provider's unique position on the liquidity curve. But the story didn't end there. The position manager contract would then call back into the pool contract's on mint function. At that point, the pool contract would execute a callback to the provider requesting them to actually fund the pool with their token. In response, the provider had to transfer both tokens to the pool to complete the process and receive the liquidity position token. As you can see, this design can easily cost 300,000 to 700,000 gas units. At that time, it made sense given the technology available, but with new ideas and improved efficiency, it was a time for a rethink. That's where Uniswap stepped in, reimagining how pools are created and managed. Let's take a look at how version 4 does it for us. After understanding how Uniswap 3 created liquidity pools, let's explore the significant leap Uniswap 4 took to make things more efficient. In version 4, Uniswap adopts the singleton design pattern in pool creation, where the pool manager contract initiates and stores the state of all pools. Pools only update their state stored in pools manager storage instead of deploying a new contract. By default, the pool manager is locked except for pool initialization. All other operations, like minting positions, modifying liquidity, settling, burning NFTs, or swapping, require unlocking the pool manager first. With this efficient design, Uniswap reduced gas costs dramatically and simplified pool management. Now, let's see how liquidity is managed in Periphery Module. Uniswap 4 Periphery Module is powered by the Position Manager contract. This contract acts like the remote control for the liquidity management, giving providers the tool they need to mint or burn their position tokens. The Position Manager also tracks each position as an NFT, letting providers keep a unique record of their liquidity. Unlike older versions, version 4 makes it simple. When liquidity providers add liquidity, fees automatically get credited to the pool. On the other hand, when they withdraw liquidity, those fees come straight back to them. No extra step needed. It also introduces two key operations. Take is to withdraw tokens from a pool or a swap, and settle is to pay off any tokens owed to the pool. But here's the catch. Position Manager checks if the pool manager is unlocked before running any of these actions. Whoever unlocked the pool manager can run any liquidity management operations they need. Position Manager is also designed to be super efficient. It uses a command-based approach where you define the action you want, encode its parameters, and then combine any number of actions into a one single transaction using the modify liquidities function. So instead of sending multiple transactions, liquidity providers can handle everything at once. Speaking of efficiency, let's step back and look at how version 3 handles swap. Imagine a user wants to swap ETH for USDC in a single hop swap. A single hop swap means that the entire swap occurs within one pool. The user sends ETH to Uniswap 3, and since it doesn't support native ETH, the swap router deposits ETH into the wrapped ETH contract to wrap it. The router then transfers the wrapped ETH to the designated pool. The pool calls transfer on the USDC contract to send the equivalent amount of USDC to the user. But what if you as a developer wants to integrate Uniswap 3 to facilitate token swap for your users? When you initially set up your smart contracts, you approve the router on the wrapped ETH contract. So when your users send you ETH, your contract deposits the ETH in the wrapped ETH contract, and since the router was already approved, it can pull the wrapped ETH and transfer it to the designated pool. The pool then calls the transfer on the USDC contract to send the equivalent amount of the USDC to your contract. Finally, your contract sends the USDC to your end user. As you can see in every swap, there are multiple calls to external contracts, and the fact that the native ease was not supported adds up to gas consumption, especially in more complex swaps or a multi-hop swaps. But in Uniswap 4, Universal Router changed the game by streamlining swaps across all pools while also supporting native ease. Version 4 designed the Universal Router to efficiently handle trades across version 2, 3, and 4. It also integrates Permit 2 to eliminate the need to approve the router for token transfers. It adds an extra security layer of signature and time-sensitive verifications. It also facilitates the migration of liquidity from version 3 to version 4 without token approvals. And as the rest of the modules, the Universal Router checks if the pool manager is unlocked. Unlocking the pool managers allows swaps to take place. Transactions are encoded as commands, where each command can represent a set of actions, and each action has a range of parameters. When properly encoded and in the right order, these commands can be chained within one single transaction to execute a customized workflow. Now let's experience how version 4 efficiently saved tremendous gas by implementing the same swap example we had in version 3. The same user we have send ETH to the Uniswap 4 protocol. The universal router routes the ETH to the designated single pool because it supports native ETH now. The pool calls transfer on the USDC contract to send the equivalent amount of USDC to the user. On the other hand, from a developer perspective, integrating Uniswap 4, your users send ETH to your smart contract, which in return forwards the ETH to the Uniswap protocol. Uniswap protocol use the router to credit and send ETH to the designated pool. The pool then calls transfer on the USDC contract to send the USDC to you, and you send it back to your user. You can tell the significant difference Uniswap 4 made in reducing the calls to the external contracts in just one swap. Before we get to multi-hop swaps, we need to explore some crucial concepts and security checks implemented by Uniswap 4. Have you ever wondered how Uniswap prices a swap? Well, think about it. As liquidity varies at different price points, the price impact of a swap depends on the liquidity available at a given price. More liquidity means lower prices, and less liquidity means higher prices. What happens if your transaction takes too long to execute? One of the functional parameters user must set when executing a swap is the deadline. If your transaction is executed after the deadline, the swap is automatically cancelled, and that's called expired transaction. But why might a swap not execute at the expected price? When you submit a swap, it sits in the main pool until picked by a validator. During that time, prices may shift, and that's what we call slippage. But how Uniswap protect users from drastic price changes? The maximum price deviation a user is willing to accept while waiting for their pending transaction to execute. If the prices moves outside this margin, the swap will fail. And that's what we call slippage tolerance. So what happens if you get fewer tokens than expected? Uniswap provides an estimate of how much a user should receive. If, while pending transaction, the anticipated output falls below the user's slippage tolerance, the swap fails. Another question a swapper would ask himself: is he selling or buying with a specific amount? We get two types of swap: the exact input swap, where the user swaps in the exact token amount and willing to receive any amount above the minimum as an output. How to get exactly what you need. That's the second type of swap, which is called exact output swaps. This happens when user swaps in the maximum amount of token to get the exact amount of token in return. Now that we have set the stage with these key concepts, let's dive into how Uniswap 4 applies them through a real-world mechanism. Now we will implement a multi-hop swap on Uniswap 4, where the swap takes place in more than one pool. The user sends ETH to the Uniswap protocol. The router then deposits the ETH into the ETH and DAO pool. Next, the router calls the swap on the USDT and DAO pool. This swap debits DAO from the first pool and credit DAO into the second pool. For the last hop, the router calls swap again on the USDT and the USDC pool. This final swap debits USDT from the DAO and the USDT pool and credits USDT into the USDT and the USDC pool. The swapper finally receives the USDC from the USDC and the USDT pool. Throughout these steps, Uniswap only updates balance internally without calling the actual transfer function on the DAO and the USDT contracts. It's like a bookkeeping on each pool involved in the swap. This efficient internal balancing is what Uniswap calls flash accounting. Another new concept Uniswap 4 introduced is delta. Let's say a liquidity provider has a pool with 100 USDC and a 75 USDT, and he wants to add liquidity of a 75 USDC and 100 USDT. Previously, this would require multiple transfer between the USDC and the USDT contracts, each costing extra gas. But in version 4, the provider would only need to swap 25 USDC for a 25 USDT, which Uniswap calls delta. In Uniswap 4, the swap and the modified liquidities are bundled into one single function, saving on gas and complexity. Flash accounting tracks only these deltas, and all these deltas must be settled before unlocking the pool manager contract, meaning neither the pool manager owes tokens to the address unlocking it, nor does the address unlocking it owes tokens to the pool manager. At the end of our tutorial, I would like to thank you for joining me on this deep dive into Uniswap 4. If you found this breakdown helpful, don't forget to like, subscribe, and share it with fellow builders. Got questions or want to see a deeper dive into a specific topic? Drop it in the comments below. And stay tuned for more insights and hands-on tutorials. Thank you for watching.